Hello everyone, this is Carl with Lunchbox Sessions. Glad you could join us. Welcome to our fourth and last live stream of the season on intensifiers and accumulators. Great to have everyone with us today, and once again our thanks and gratitude to all of you out there, individuals, companies who share knowledge with us. There is continuously so much to learn in the field of hydraulics, so the learning never stops. It's fun. We certainly enjoy it here. Just as a reminder, some of the procedures and demonstrations that you'll see shown here today, the time we'll have together won't be enough to ensure your safety if you have limited experience and training in hydraulics. So if you're going to work with pressurized circuits, if you're going to work with accumulators, intensifiers, if you're looking to make circuitry work in a similar way to what you'll see in our demonstrations, make sure to work with a mentor, with a pro if you're still relatively new to hydraulics, and get the training you need to make sure that you can work as safely as possible with hydraulic components and systems. You'll notice on Lunchbox Sessions in our live stream page, or if you're with us on the YouTube channel directly, that there are some links that take you to websites, to PDF files that are lined up with some of the components that you'll see us using here today. So if you're curious about some of the models that we're using, you'll be able to link to those and do some further learning that way. If you're on your Google services or logged into your YouTube account, you'll be able to use the live chat and let us know where you're from and ask questions if you wish. If you have questions directly related to intensifiers and accumulators and the topics we're handling today, we'll try to catch a few of those, as many as possible. If you have other questions not related to accumulators or intensifiers today, then general questions or other topics in hydraulics, then feel free to send those to us by email, info@lunchboxsessions.com, or look for me on LinkedIn. I'm pretty easy to find, Carl Dyke, Industrial Teacher. All right, a shout out to our friends today at fluidpowerworld.com. And Fluid Power World is your resource for components and for design and engineering knowledge. The Fluid Power Technology Conference continues with excellent virtual events. See the events tab on fluidpowerworld.com. Our major sponsor today is IC Fluid Power. IC Fluid Power is a global hydraulic component sourcing company bringing you easy access to dozens of high-quality, high-precision European manufacturers. Save significant time and resources in your machine design work and hydraulic problem solving with our long-established direct relationships. Since 1989, we have provided technical and engineering expertise to solve your unique challenges, combined with logistics and sourcing strategies to minimize cost, and offering local service and support with a smile. For more information, visit icfluid.com. All right, great to see so many of you with us today. We see we've got participants from Ghana and from Brazil and Oman, so welcome. India also, great to have you with us. All right, hydraulic intensifiers, pretty intense topic. All right, let's have a look at a three-dimensional model just to get everybody acquainted a little bit with some of the internal components, some of the excitement that is packed into a device that we'll be talking about today called a hydraulic pressure intensifier, sometimes known as a hydraulic booster. And of course, surface area is the game at play. And as you likely know, if you apply a fluid at a certain pressure against a surface area, perhaps the surface area is shown on the bottom here in green, and then mechanically transmit a force along the piston to a smaller surface area where fluid can be pushed as the piston is extended. With that smaller surface area comes the intensification, where the pressure can be stepped up in relationship to the ratio change of surface areas from the bottom to the top. In this example, perhaps 5 times as much surface area on the inlet piston at the bottom, where the pump supply pressure is made available, compared to, say, a single unit of surface area at the top, where the intensifier discharges pressure at the HP, the high pressure port, traveling to where it needs to go next. And of course, the key reason that pressure intensifiers are selected as a component for hydraulic systems is that at times a portion of the hydraulic circuit needs to operate at a pressure much higher than what is typically available in the hydraulic system. So a typical hydraulic system might be maximum at around the 3,000 psi or 200 bar mark. That is a typical high-level value for normal hydraulic systems, but perhaps somewhere along the way there is one application within the hydraulic system where a much higher pressure is needed. Quite often that has to do with holding or clamping, work clamping in a CNC machine center. A high force is required and higher pressures are necessary to achieve that. Or perhaps it's for a tool, a cable cutter to cut through wire rope. Steel cable, high tensile steel cable is quite often a tool that requires a pressure that needs a pressure quite a bit higher than what is typically present in a standard hydraulic system. And so, why build up the entire hydraulic system to be capable of working at pressures perhaps up to 10,000 psi, in some cases even higher, when that is going to require a lot of specialized design, high pressure capable components, a lot of additional cost. So in certain applications, it's advantageous to just install the high pressure intensifier at one particular corner of the hydraulic system where that higher pressure is needed. And so our system here, our 3D model, is a very simple one in that we're demonstrating on a simple hydraulic cylinder that perhaps extends quite simply in its early portion of its stroke, but then comes under the need to work with higher pressures. And we're just using a generic model of a spring to demonstrate the stepping up of pressure. So if you're watching that P gauge, I'll just keep playing this over and over a few more times. If you're watching that inlet P port gauge at the bottom left, what you will notice, of course, is that that's at a lower pressure, and then the gauge at the high pressure port as the main piston inside shuttles back and forth, providing the stepping up of pressure as required. If your hydraulic fluid has a fair amount of entrained gas or air in it, or if there is some internal leakage to seals, perhaps piston seals, if there are some pilot circuits running in the downstream portion of the circuitry, then the main piston inside the intensifier will continue to stroke back and forth and reciprocate, taking in a charge of oil via check valve. We'll see this in schematic form in a few moments, but you see the 2 check valves in green inside the body of the intensifier, and those check valves are allowing the reciprocating piston to access a fresh supply of oil, while that top check valve holds shut during the reciprocation, where the piston takes in another charge of oil from the pump, and so forth. So it's an easy one to understand how it works. Of course, there's another spool valve sitting slightly to the left of the main piston inside, and that spool valve is shuttling back and forth to change the position of what happens with the oil as it enters into the main piston, either to direct pump oil to the bottom of that main piston where you see the 5x, the 5 times in green, or to allow the main piston to retract back to its resting position and draw in a fresh charge of oil from the P pump supply line. So yeah, a couple of little parts are moving back and forth in there continuously until the requirement for the intensified high pressure on the output port has been reached. And perhaps this will be easier for some of you to understand. If we have a look at a few of the pieces here on the bench, you'll see that our intensifier piston in our model is a single piece. And of course, in many cases, the piston is split into two to make it easier for assembly. So what is on the bottom here is often referred to as the high pressure piston, the low pressure piston, and at the top, of course, the high pressure piston. Let's switch over for a moment here. We'll have a look at a few pieces just on the workbench here. Here is the body of an intensifier. It's all been taken apart. There's a couple of integrated check valve assemblies that match up with what you saw in the three-dimensional video. There is the shuttling spool that moves back and forth to change the reciprocating action of the main piston. And maybe I just lost my connection there for a second. There we go. I think we're good now. And there is our main stroking, our main reciprocating piston. So the larger surface area, the low pressure piston on the right, and this is the typical two-piece assembly, easier for component assembly. I'll just try to pull a better focus there for you. There we go. And then of course the high pressure piston on the left where we discharge out to our application circuit, our cylinder, our cable cutter, our work holding clamps in a machining center perhaps. So yeah, not a ton of pieces on the inside, but of course a lot of very fine machining and honing work to make sure that the clearances are minimal, that the device can work with a great deal of accuracy. There you could see a 3-piece body. And so there's the typical pieces of a pressure intensifier. All right, we'll go and have a look now at equipment on the training panel, and we'll do some demonstrations of live circuitry. All right. All right, so over here I've got some equipment assembled, and you'll see that we've got a couple of hydraulic pressure intensifiers, but we've only got one of them hooked up today, and this one is a 4-to-1 pressure intensifier, so we're expecting to be able to produce on the outlet pressures that are 4 times higher than what are entering on the inlet. The P port in this case is over on the right here, and of course there must be a connection back to tank, because as the shuttling valve is moving back and forth, there is a need to vent a very small amount of fluid, and the area between the high pressure and the low pressure piston is a gallery that is always connected to tank as well. So a very small amount of fluid is continuously moving back to tank as the device shuttles back and forth on the inside. In our case, what we're going to see is that we've used a very small diameter hose to connect the high pressure output of our intensifier to a short stroke cylinder, just a few inches, and our short stroke cylinder, our single acting cylinder, it's single acting because we've connected the rod side to tank, so that's vented, but we're pumping the intensified pressure into the top port as seen here on the C12 schematic symbol. So we're going to pump our intensified pressure in, and then of course we'll be working against a spring. So a spring will be compressed gradually, and of course as we select a higher and higher inlet pressure, we'll be able to see the effects of that being intensified. And so to help us understand better what's happening with intensified pressure, our gauge on the right will be the inlet pressure on the P port coming in to the bottom of the intensifier, and the gauge on the left will report our intensified pressure. In fact, let's go back to the computer for just a moment and make sure that we understand a little bit about the schematic that we're going to be using. We've got a few different schematics. You can access a few of these resources as well. Here, I'll just go back in Lunchbox Sessions for a second to show you where we are in our menu. We have a session called Hydraulic Accessories, and there it is. And so you'll be able to find some of those resources there. This particular circuit, these are just some circuits that we use for training, but they help us understand how you might choose to connect to an intensifier and deal with, of course, the reality that you may need to let that cylinder return to its original position. And of course, the intensifier has a pair of check valves in it, so the intensifier itself does not wish to allow pressure on the outlet to bleed back down to tank. There's check valves to prevent that. The dark gray box that you're seeing on screen is the boundary of all of those components we were looking at a moment ago on the bench top that are inside the intensifier, and now we're showing them to you in schematic form. So let's just start off and extend our cylinder, but let's just use the directional valve in the bottom right of the schematic and just use it to generally use the regular pump pressure, the system pressure, to extend our cylinder. And our cylinder working against a spring, and so perhaps that's not adequate for our final needs, especially if it's work holding or if it's a tool of some kind. And so perhaps now what we need to do is intensify. So again, the bottom directional valve, I'll energize the solenoid, and now we'll direct the system pressure from our hydraulic power unit. We'll direct that into the intensifier. And now what you see, of course, is the action that you would expect as long as there is a draw for volume, as long as there is a room in the cylinder or whatever our downstream circuitry is to consume flow. The intensifier main piston will continue to shuttle back and forth until the intensified pressure is reached. And then, of course, the reciprocating piston will stop and the intensified pressure is held. Okay, in our case here, of course, we may need a way to allow our cylinder to retract, so that upper directional valve, in this case, will allow that, and the spring, in a single acting type of way with our cylinder, will return our cylinder back to its original position. Okay, and let's have a look at a second schematic that's here. This one you'll have access to if you're in our session on accessories, and go ahead and try that out. This is just a circuit that we put together just for today to demonstrate what components we've got. So we're working with a 4-to-1 intensifier, as I pointed out in the video images a few minutes ago. And just to give us a lot of control over the amount of pressure entering in at the P port, we installed a pressure reducing / relieving valve that is operated by a proportional signal. And so as we change the signal that's driving that proportional pressure reducing valve, we've got 1,000 psi available to us on port 2. But as we activate that valve, we'll be able to draw in on the P port, enter in on the P port of the intensifier with pressures between 0 and 485. That's the parameter pressure value ranges for this Sun PRDP valve that we installed. And so we'll be able to just very carefully introduce pressure on the P port and then watch and see the intensification. Okay, those are the two digital gauges I was showing you a moment ago. The source pressure versus the intensified pressure, and then we'll see our cylinder extend against the spring as we dial up to higher and higher pressures. The needle valve is there so that we can choose to allow our cylinder to return, or to let us simulate that perhaps there's some internal leakage in our downstream circuitry. If our cylinder is very large and perhaps there's an ambient amount of leakage around the piston seal, whatever that might be, as leakage develops, The reciprocating piston inside the intensifier will begin to stroke back and forth and work to push fluid out and maintain the intensified pressure. And of course, in the symbol here, you see very clearly depicted the idea that there is a larger surface area on the low pressure side of the piston, and then a reduced surface area at the top, which allows us to intensify pressure. There's our shuttling spool, which will be in charge of allowing our piston to move back and forth as it reaches the end of stroke. The shuttling valve will be exposed to a low pressure area and will shuttle back into position to receive a charge of oil from the P-port coming in from the pump and stroke forward once again. Here, let's operate that one. You're welcome to do that as well if you're using this resource on lunchbox sessions. And so what you'll see here, of course, as we introduce a higher and higher signal and bring up the pressure entering in, coming in from our source, we see the intensifier beginning to stroke back and forth and multiply the pressure available. And we see our spring cylinder being compressed, and perhaps in this case we're going to take our cylinder all the way to the end of stroke. But what you're seeing if you watch the two available pressure gauges is that 485, our maximum allowable pressure that we can introduce with the pressure valve we put there just for experimental purposes, has been multiplied times 4, and so our pressure is intensified. It's about that simple. Once again, if leakage develops, I'm just going to open that needle valve there at the top. Right away, the intensifier will become active and work to maintain the intended pressure as best it possibly can. Of course, if the leakage becomes very large, it's not reasonable to expect that the intensifier will maintain 4 times the pressure from the inlet. It will struggle to do so as the leakage path becomes larger and larger. And of course, that's not the intended functioning for the intensifier to demonstrate its best capability. Okay, so I'll eliminate the leakage once again. All right, so let's head back over to the experiment on the training panel. And now you have a good feel once again for what's happening to our intensifier on the right here. I'll just pull a focus again. There we go, a 4-to-1 intensifier. So just because the arrangement of what's on the schematic versus what's here on the panel might seem a little different, I'll just remind you once again that our inlet pressure is coming in here to the P-port, which we've oriented on the right. Our drain to tank is here on the left. And of course, outlet from the high pressure port. Outlet from the high pressure port is here at the top. It's labeled HP there, as you can see. Yeah, pretty straightforward, okay? And again, a skinny hose because we're not really moving much flow, but a high pressure rated capable hose, and that's moving into the base end of our cylinder to extend it. There's the symbol once again, and our cylinder will extend against spring resistance, which is a good thing to have in this case. It allows us to see very clearly the effect of pressure intensification. Okay, just to remind you once again of the two digital gauges, the one on the left is our intensified pressure. You'll see that quite clearly in a moment. And the one on the right is our source pressure and being delivered to the P-port on the intensifier. All right. And then so for the valving, as I mentioned, we're going to use a pressure reducing / relieving valve that is proportional in nature. You could see on the solenoid symbol the diagonal arrow passing through the solenoid, so we know it's proportional. You could see also the infinite positioning bars. Very easy to start to look at a valve symbol like that and say, oh, is it a proportional directional valve? No, that is not at all its intention. And if I move over to the other side of that same symbol, perhaps you'll see more clearly that there is a pilot port on, or a monitoring, a sensing passage, the dashed passage that you see on the outlet. Number 1 is the outlet, and you see that that outlet pressure is acting on the poppet inside this valve. And so this valve will remain very active in a very short stroke. The symbol would imply that maybe there's a lot of movement taking place inside, when in fact the internal valve element for a valve like this is perhaps only moving a millimeter or two at the most, perhaps a 32nd or a 16th of an inch, a very small amount of movement. The particular valve we chose has an onboard amplifier card, and of course it's always about a variable current signal being sent to the solenoid, but since there's an amplifier on board, we're just going to be sending a control signal. The amplifier will make the finished current being delivered to the solenoid, and so typically a control signal might be sent from a PLC. We would typically do that. In this case, I'm just going to use a small jog device that is all set up to go. We still have 24 volts being sourced separately to provide sufficient drive current going to that valve. And so in my little jog box, and just due to the way we chose the options for that pressure valve, ours requires a control signal of 0 to 10 volts in. And just because I know I'm not going to see much response, I'm just going to move up to about 2.5 volts. It's kind of about the beginning range for noticing something happening with this valve. We'll turn on our hydraulic power unit and get ready. And so up comes our system pressure, and our system pressure is rising slowly today because we've got an accumulator also in our circuit that's being charged with oil. We'll get to that in a few moments, but there is our system pressure. So that is our pump now off stroke. Our pressure compensated pump is now off stroke. That's our system pressure available to us. I'll bring our proportional control into view as best as I can. And so there's our two pressure gauges available to us. And so I'm going to dial up a little bit of voltage. I've got a lot of things in my hands here all at once, but I think it'll work. Okay, and so dialing up to about 3, now 4 volts. And we're starting to see the action of the circuit, but of course we're at a very, very low pressure range, and it's just in the very early stages, and so we're not necessarily expecting to see a perfect 4-to-1 intensification at this lowest pressure range, but I'll just dial up a little bit more, and we'll see again the pressure being introduced on the P port on the right-hand gauge and being intensified on the outlet of the intensifier on the left-hand gauge. So I'll just back out a little bit here and continue to dial up to a higher signal, just coming up on 5 volts. And of course, if you're watching the spring being compressed, you know, that is a very clear depiction of the force being made available by intensified pressure. And you're seeing that spring being compressed as we continue to introduce. And of course, I'm not working in a high pressure range. I'm very close to hydraulic hoses, concerned about general safety. So just staying in lower pressure ranges for very close demonstrations. And so you'll see the pressure being intensified. But because we're in such a low general range, not always easy to see it exactly as 4-to-1. It's approximately 3.5-to-1 the way it is set up at the moment. And continuing to bring up my proportional value to 8 volts. And of course, as you know, this particular pressure valve that we involved here tops out at 485. And I'll back away a little bit so you can continue to see the spring being compressed. Just giving you a general idea of the action of that with the gauges for us to start with. Okay, and so now I'll back off that. Actually, I'm going to leave it set at 10 volts for a little bit. Maximum value to our proportional. I'll bring the camera back out a little bit. I think you can see a number of things now. So if you were looking at that schematic, that live schematic with me, and I think you can still see the pressure values for the most part. Just doing a little focusing there. And so if I start to develop some leakage in the circuit, I'm not sure if you'll be able to hear it, but I think you'll certainly see the hoses bouncing. You'll certainly know now that the pressure intensifier has gone into action to try its best to make up for internal leakage in the downstream circuitry. And it's doing its best to push fluid out on the high pressure, reduced surface area piston and continue to bring up the pressure as best it can. Of course, it's going to struggle to maintain the rated intensification if we're in a scenario where the leakage is substantial. But the rate at which you see the hoses bouncing up and down is the rate at which I can hear the clicking as the spool, the main piston shuttles back and forth, taking in a fresh charge of oil through the check valve and pushing it out on the high pressure port in an attempt to try to maintain high pressure. So ultimately, of course, you want to minimize leakage on the downstream side. It's not typical to find a lot of internal leakage for high pressure tools, but even if a small volume leaks over the period of several minutes, the intensifier will immediately shuttle, even if it only just shuttles once, and will work to squeeze out intensified oil on that reduced diameter high pressure piston and hold the required pressure on the downstream side, especially if it's work holding or something like that. On a work center, on a machining center, one would not want to see it come loose. So the intensifier is busy doing that. In fact, while we're at it, I'll take you over to analog gauges on our hydraulic power unit, and you can clearly see that with the consumption happening in little shots as the main piston reciprocates back and forth, we're seeing that there are small pressure drops and system pressure is fluctuating a little bit. And then, of course, we have a very small pump here. We're only working with a pump that comes up to a gallon a minute. In fact, we're only at, on our variable displacement pump, we're only at about 1 liter or a quarter of a gallon per minute at this present time. So on a very large hydraulic system, where a very large piston pump might be supplying many different circuits, this might not be as noticeable. Or maybe this will be a good way to segue at some point to our lesson today on accumulators. So if I just take a moment to introduce an accumulator that I have all set to go and allow that to be teed into our supply line. There we go. Just introduced an accumulator, and now the effect of the little pressure changes seen at the power unit are much smaller. If we come out to have a look at the hoses heading up to our application cylinder, we can see that they're still shaking. The accumulator is doing its, or the intensifier is doing its best, but further back in the rest of the hydraulic system, the accumulator has smoothed things out, and that might remove some ripples, some minor pressure variations that might be undesirable elsewhere in the system. And again, this is a very small system, so it's easy to see the effects. This is a small series of general purpose intensifiers. This one will consume at maximum 8 liters per minute, or roughly 2 gallons per minute. And you're not going to get all of that 8 liters on the outlet either. You'll get a slightly reduced percentage of that 8 liters in due to the minor amount of return to tank flow that occurs. But again, if you're going to need a much larger volume to extend a cylinder or to work with a higher internal leakage at a higher rate, then there are sometimes other series that jump you up, other model series that jump you up to 20 liter per minute ranges, roughly 4 or 5 gallons a minute, and perhaps other intensifier series as well. So this is just a very small series for general purpose, and it gets it done for a lot of circuits. These particular ones are Scanwell intensifiers from a manufacturer in Denmark. All right, so that gives us a bit of a demonstration today on what the intensifier is up to. And of course, let's just be clear that once again, if I eliminate leakage in the system, I was simulating it with the needle valve open. If I close in my needle valve, the same one that showed up in our live schematic, we'll see that the hoses will stop shaking and that our intensified pressure stabilizes, and it's roughly 4 to 1, 3.5 to 1 in this case. We're using this intensifier in the smaller or the lower pressure range of what it's capable of. This particular intensifier could easily produce up to 10,000 psi on the outlet. All right, let's stop our power unit. Maybe we'll take a moment and see if there are some related questions that should be answered. Okay, so questions coming in. All right, Anmol is asking about calculating accumulator size in an integrated system for pressure drop. Yeah, we'll get into that in a few moments, so hang on to that thought for a moment there. So that's good. That's a really great question to ask about. And Andrew Middleton is asking, what's the red sealant you're using in the fitting for those gauges? Hey, Andrew, good question. Did you see some red sealant? Ah, yes, you did. I would have to double check, but I believe it's a Loctite product, and I cannot remember right now what number it is, but it is a sealant meant for work with hydraulic fittings. Don't have that one right at the tip of my tongue at the moment. We'll see if we can figure that out. All right, just let me catch up with my notes here for a moment, make sure I covered off on everything we needed to do there. All right, so let's switch over to the world of accumulators. And I think what you just saw a moment ago is that an accumulator can be used to smooth out pressure ripples in a hydraulic system. It can also be used to be a shock absorber. That's not an uncommon application for a hydraulic accumulator. And so that's a very different device from an intensifier. So if a portion of a circuit needs higher pressure, that's not something that an accumulator does. That's a job that's great for an intensifier. If, on the other hand, what you're looking for is a pressure shock absorber, or a very popular application is to use an accumulator to supplement the flow, the maximum flow rate available by the pump, to give a little boost to the maximum flow rate available in the hydraulic system for a portion of a machine cycle when a higher flow rate is desired and needed and the pump isn't large enough. And you might say, well, just put in a larger pump so that it can provide that flow rate. Yeah, that's always an option. But if you only need that slightly higher flow rate for perhaps 5-10% of the machine's duty cycle, then that could be an unnecessary inefficiency that can make the system more expensive, larger, more energy consumption, and so sometimes not necessary. And so, to use an accumulator to supplement the flow available from the pump and provide a bit of a flow rate boost for a small period of time, generally speaking, it's still efficient, more cost effective if you're going to use the accumulator as a flow supplement for up to maybe 25% of a hydraulic machine's duty cycle. Beyond that, probably the realistic aspect of thinking that the accumulator will be able to provide you with that efficiency is no longer there, and it would be more reasonable instead to put a larger pump into the system. Okay, I think our transmission bandwidth has dropped off just a little bit, so I'll speak a little slower. Not that that helps, but it just will hopefully prevent some of you from losing what you're hearing, some of the content being covered, and it should pick up hopefully and correct itself in a moment. All right, so when we're talking about accumulators, you know, there's a couple of different styles. Just going to see if I can get my camera reconnected here, my portable camera. It's just giving me a little bit of difficulty. So I'll see if I can get that corrected here for you. And I'm not having any luck, but just one more moment. We'll see if we can get our issue solved there. And we'll probably need to restart that. All right, hopefully I'll get my portable camera transmitting here again in a second, and then we'll look at some accumulator parts here on the bench top. Just a minor connectivity issue for a moment there. Just try once more to get that restarted. All right, my mobile camera is giving me a little bit of difficulty today, and so I'll work with the large camera for a moment, and we'll just look at the big parts first, and perhaps we'll be able to resolve that. An accumulator, of course, has a very large, or has a very heavy duty, doesn't have to be large, pressure vessel. The walls of the accumulator are pretty thick. It's a pressure accumulator. If it's meant to come up into thousands of psi, it's a pressure vessel. Of course, this is a bladder style accumulator, and that's not the only kind of accumulator out there. There are also diaphragm style. I don't have one of those taken apart. I don't have a piston style accumulator either, but bladder accumulators are certainly popular. Sometimes the piston accumulator is the better choice for those who wish to have very high flow rates. If there's concerns about low temperature, it's often thought that the piston style accumulator will do better, because then the flexible bladder material isn't constantly being flexed in a very cold scenario, which can make the life of the bladder a little difficult to survive. But of course, that's not always true either. What you find out when you're shopping for accumulators, you find out that Buna N is a very typical material to have the bladder made of, but, and if that's not good enough for the temperature ranges you work in, then of course there's low temperature Buna, which allows for a much lower temperature range, and then there's fluoroelastomer types of bladders, which can take you up to higher temperatures. There's hydrogen. I can't remember all the particular advantages of those different materials, but when you're shopping for accumulators and you're looking through a manufacturer's specification sheets, you will often find that you have a number of options available to you, and of course they will be a little bit more expensive than just Buna N, but they do allow you to have a more expanded temperature range. And the advantage, of course, of a bladder accumulator is that it's much more responsive than a piston accumulator, in that you don't have a large mass, a steel mass, the piston, to need to get moving when there's a charge of oil coming in, when there's pressure spikes. So the flexible bladder accumulator is generally thought to be a lot more responsive. And of course, size for size, the bladder style accumulator is lighter weight than the piston style accumulator of equivalent size, because you don't have that heavy steel piston. So that's part of the fun of dealing with the selection for accumulators. If there's going to be a scenario where the accumulator can't be mounted vertically, that's not recommended for energy storage to move out of vertical, but for shock absorption, quite often manufacturers of accumulators are fine with having you mount the accumulator horizontal. Then bladder or diaphragm is going to be the only way to go. Piston accumulators generally meant to stand vertical only. All right, at the bottom of a bladder accumulator is this poppet valve. And that poppet valve is there to close up if the bladder makes it all the way to the bottom. Hydrogen gas, which we'll talk about, nitrogen gas introduced from the top, pushing down on the bladder to extend it, and pushes down until that poppet closes, and that keeps the bladder from extruding out into the outlet port of the accumulator, outlet port of the accumulator and into the hydraulic line, which would be very damaging. Your bladder would be wrapping around all kinds of solid edges that you don't wish to have that encounter. This is not meant to be cycled continuously all day as the machinery runs. If your bladder is constantly pushing down on the poppet valve during the normal cycling of your machine, then something is not correct. Either the bladder is not sized correctly, the accumulator is not sized correctly, or the precharge gas pressure, the nitrogen precharge gas pressure is not correct. And so if you're continuously pushing down, if that bladder makes it to the bottom and continuously pushes down on the poppet, then that's not a great scenario, because that will be still a wear or a stress point as the bladder wraps over the top of that poppet. So not meant for continuous cycling all day long. Something's wrong with your precharge pressure or the sizing of your accumulator overall if that's continuously having to cycle. And okay, and then let's see, what other parts should we talk about? Well, I guess that pretty much covers off on some of the pieces we need to see there. Yeah, nitrogen gas, of course, is introduced through some type of valving at the top, and that allows us to precharge, which is the process of pumping gas into the bladder, and that's different from oil coming in from the bottom, which is generally thought of as charge. Charge when oil is entering from the bottom, discharge when oil is leaving from the bottom of the accumulator, and precharge is what we're talking about if we're putting gas in from the top. All right. That's a good scenario for us to think about there. Unfortunately, I don't think my roving camera wants to cooperate today, so I'm going to have a little bit of a tough time getting close to our circuit on the panel. I'll see if there's anything I could quickly do to get that back in action, but it doesn't look like we're having luck with that. Just going to keep that here in case that... All right, let's go to a simulation here in Lunchbox Sessions where we can have a look at accumulator functions. And of course, it's always great on an accumulator to have some type of valving that can allow you to blow down the charge oil in the accumulator when you're done working with your machinery, if you're shutting down for a maintenance cycle and what have you. Hanging on to stored energy in the form of pressure oil in the accumulator is an unfortunate place to end up in. Many stories that we hear as we go about our travels often revolve around someone saying, we forgot the accumulator still had charge oil, we took off some hoses to do maintenance and we got wet. And of course, if nobody got hurt, perhaps as time goes by, that's seen in a humorous light. But of course, it's not humorous at all. It remains a very serious safety hazard that needs to be addressed. So in many a situation, valving is connected in well-designed machinery that allows you to bleed down. Okay, let's just charge our accumulator here. We'll put some precharge in. We'll talk about the precharge here in a moment because that was a question that came up, and sizing was also a question. And now as I turn my circuit on, I'm going to fire up my hydraulic pump, which is apparently 2,500 psi rated hydraulic pump, pressure compensated pump. And so we see that eventually, even though I started off with only 500 psi of precharge, in this case, soon as we push oil in and charge the accumulator, eventually what we see on the gas gauge, if we left one connected on top, eventually what we see on the gas gauge is equilibrium. That makes sense, right? As hydraulic pump is pushing oil into the bottom of the accumulator, the liquid is squeezing the gas precharge bladder on top and eventually bringing our nitrogen gas to a high pressure that is in equilibrium with the hydraulic pump pressure control, pressure compensator in this particular case. Okay, we'll run our cylinder back and forth a little bit. First of all, I've got to find my pilot valve that allows the accumulator to enter into the circuit. So this particular control block that was mounted on a client circuit allowed for the shutting off of the accumulator from being discharging its pressure oil into the circuit. So I've activated that now. There's a logic cartridge involved there. And now, of course, when I go to extend and retract the cylinder, we find out that if the draw for hydraulic fluid is such that our pump makes it to its maximum flow rate, which you see there, if you're watching the pump and you see the diagonal arrow going to Q max, you'll realize that our pump has gone to its full displacement, and so there's extra flow that could be consumed if available. And of course, it's available from our accumulator. And so our cylinder is able to move as quickly as possible. If you're watching the accumulator, the flow, the volume that's stored in the accumulator drops down a little bit during the cycling of the cylinder, and then when we hit the hold position, the center position on the directional valve or the cylinder deadheads, then we see that right away the accumulator moves back to its fill position. Okay, from a safety point of view, if we were to shut off our pump, then typically in a good design scenario, we see that the blow-down directional valve was de-energized and through a small orifice so that we don't have a violent flow of hydraulic fluid which could do damage, bleeding down through an orifice automatically when the machine shuts down. That's always a highly desirable scenario to work with for a safety valve below an accumulator. All right. Let's have a look over here on the training panel. What you'll notice on our system here is that we have a safety block that is a little bit more manual in nature. In this particular case, there is a manual blowdown valve that lets us open up and bleed off whatever charge oil might be held inside the accumulator, and then also a lockout valve which blocks the pump inlet line from having access to the bottom of the accumulator, and we can even put a lock in there and do our legally required lockout and tag out if we're going to do services on a hydraulic system, remove hoses and what have you. So a safety block is always a great idea. Many manufacturers offer them. Sometimes a machine designer comes with other types of valves to achieve something similar, but having that safety block as close as you possibly can to the inlet of the accumulator is always your best bet. I'm going to return that to the open position. All right, one of the questions that we had that came in earlier was about sizing. And of course, for sizing, there are a number of equations you just simply have to go through. There's no way around that. And what you have to do is work on the basis of, if you're going to supplement flow to your pump, you need to know in advance how much cubic inches or how many cubic centimeters of fluid do you wish to add into the pump's outlet stream, and then work that into an equation that takes into account what the maximum system pressure is, what the lowest working pressure is, meaning the working pressure that will still allow all of your hydraulic cylinders to get the work done that needs to happen. And then precharge is often calculated for a flow supplementing accumulator to be 90% of that lowest working pressure that still allows the forces to be adequate in the hydraulic system. Cylinders can still complete the work they need to do forcefully. Hydraulic motors the same. Not worrying about speed at that point, just establishing that lowest working pressure in the hydraulic system that still allows for forces to be adequate. And then 90% of that is typically now your nitrogen gas precharge. So that gets calculated in there. One needs to take into account temperatures as well. So for a manufacturer such as Hydac or Parker or some of the other accumulator makers out there, if you have a look on their websites, you'll usually find recommended equations that will very quickly help you arrive at the correct size of an accumulator for the application you have in mind, which is most particular if you are doing flow supplement to the pump. Another factor that needs to be taken into account is whether or not the discharge of the accumulator, meaning the rate at which you will draw the fluid out, the liquid out of the accumulator to supplement to the pump. What you're concerned about there is whether or not the draw and discharge from the accumulator will be adiabatic in nature. Wow, that's a big word, right? Try to wrap your mouth around that one. Adiabatic in simplest terms means that you're going to allow that accumulator to push out the fluid as fast as it possibly can. You're going to open a fairly large flow valve. There is going to be a free path for consumption of fluid, perhaps to a cylinder. And in that mode, you're going to let nitrogen gas do what it wants to do, expand very rapidly. And as that nitrogen gas expands rapidly in the bladder, if it expands rapidly, if it's pushing the flow out quickly, there's going to be a cooling effect. That is what happens when gas expands quickly. And that cooling effect means that the accumulator will not be able to drive out quite as much total volume as it could, as if you metered that volume very slowly and fed it into the downstream circuitry more gradually, as though through a needle valve. And so when you're flowing more gradually through a needle valve and the gas in the bladder expands gradually, there's time for the heat exchange to take place and for the bladder and accumulator to equalize in temperature with the external environment. And then, believe it or not, the accumulator can deliver, surprisingly, quite a bit more total volume out into the downstream circuitry. So that's an isothermal application. Okay, I'm speaking in some very general terms. But again, spend some time with accumulator manufacturers' websites and with the representatives who into account the size of hydraulic hoses, size of hydraulic valves. So things start out ideal, and then quite often you move up to one size larger in the selection of an accumulator. All right, let's see if there's some other questions there I can answer from the group. Yeah, is there a gas intensifier used to charge a nitrogen accumulator? Wow, that's an interesting question. Yeah, so pre-charging a nitrogen accumulator. So it's the word pre-charge that we're after if we're speaking of the gas that is brought into the bladder from the top. That pre-charging is done usually from a high pressure cylinder that has been provided by a gas manufacturer. And so, yeah, that cylinder needs to be charged with nitrogen at a pressure quite a bit higher than what you're intending to put in as your pre-charge amount. I haven't heard of something called an intensifier to charge an accumulator, but we certainly do have clients who keep their nitrogen bottles permanently connected to a large bank of accumulators, and then valving that automatically tops up and maintains in a continuous run manufacturing environment. So yeah, that is not an uncommon scenario to end up in. And we had a question there, is this how Enerpac pumps work? Yeah, I mean, there's a number of manufacturers out there who are making various different high-pressure pumping devices. I'm not sure exactly what you mean by is this how they work, but if you're referring back to intensifiers that we were speaking of in the earlier part of the presentation, surface areas play a major role in allowing a lower pressure to be stepped up to a higher pressure. Yes, indeed. All right. Let's see if there are some other questions coming in here. So that's a brief introduction to accumulators, and I hope that's been helpful for everyone today. We'll probably wrap things up and move on. So once again, thanks for everyone for joining us for the season. We had viewers today from Canada and from Africa and all over the United States and places far away. We certainly appreciate you joining us for our shorter season this year of YouTube Lives, our live streams, and perhaps we'll have another one or two around the end of the year or New Year. We'll see if we have time for that. Oh, another question coming in here. What's the best place to install an accumulator for dumping pulsation purposes? I'm not entirely sure if I know what's being meant by that question. Danilo, but let me just try to think for a moment what you might be thinking about. If it's pulsations in the hydraulic system overall that we're worried about, then quite often that accumulator will be mounted fairly close to the pump. What we find when we're doing data logging on systems that have piston pumps, it's very easy to pick up on the pulsations from even a 9-piston style piston pump. We hear of some new piston pumps out there now that have upwards of 20 pistons in them. There are some other types of pumps out there that have over 100 pistons in them. Certainly that does smooth out the flow rate and removes natural pulsations in the system. So natural pulsations, quite often you want your accumulator to be back fairly early on in the hydraulic circuitry near the pump. If that accumulator is going to supplement flow to a number of different places in a hydraulic circuit, again, the accumulator may be right close to the pump. If, on the other hand, an accumulator will supplement flow to one particular sub-application of the hydraulic circuit, right close to one cylinder only, then typically you'll find that accumulator mounted right close to the directional valve that is going to drive one particular cylinder that needs to move at a faster speed, that is going to consume at a high rate once that directional valve is open. So I hope that's helpful, Danilo, for your question there. All right, Lunchbox Sessions in the services of CD Industrial Group is brought to you by Nathan and Crystal and Robin and Chris, Ivan, Alex, Keelan, Emily, Mark, Lenore, Owen, and Ted. And of course, I'm Carl. Our big thanks today to our friends at FluidPowerWorld.com and of course our major sponsor, IC Fluid Power. We thank you once again for joining us for our season of live streams, and we hope to see you again really soon. Perhaps, as I said, we might do one or two more near year end or New Year, but it's been great having you with us throughout the summer. Wishing you excellent health and safe hydraulic work wherever you are. This is Carl saying so long for now, and thanks for being a fan. Take care, everyone. Bye-bye.